Okie dokie. Chapter 4, I'm going to have you guys read from this section all the way down to right about here, where it says local extreme values. We're going to fill that in together. And just one little side comment, when you see that right there, that is not at all the color that I wanted. I wanted blue. When you see the IFF, that's talking about if and only if. Okay? So take a couple minutes, read this. You'll be quizzed on this tomorrow. Yes, I'm serious. You'll be quizzed. Okay, we're going to take a look at this bottom graph. We've got a function. It is continuous, and we're told that the derivative is defined at every location x equals c. This is just an arbitrary value within the interior point of the domain. Looking at this function, if I tell you that this graph has a local min or a local max at one of these interior points, I bet you can guess that the derivative is going to be, yep, you got it, 0. That's at every max and every single min. It's going to have a horizontal tangent line, and the derivative would be 0 because the slope of each of those lines is 0. So that's it for the first page. Put in the books. Yeah! All right, there are two types of extreme values. You can have an absolute or global extreme value. And this is just talking about the entire function in the domain that it's defined upon. And a local, also known as relative. This is considered regional or in the immediate area. One way to think about this is if you can picture a mountain range. If you look at the entire mountain range, the highest peak in the entire range would be considered the absolute or the global. If you look at the range and there are several mountain tops that are the highest within that immediate area, those are like local. So keep that in mind. Example 1 is asking you for each function below to identify the x value at which any absolute value extreme value occurs, and explain how this is consistent with the extreme value theorem. Now, the extreme value theorem requires that it be a continuous function on a closed domain. So for part A here, we're looking at a function that is not continuous, and it's certainly not on a closed domain. We've got endpoints here that is open, so this is not closed, and we have a jump discontinuity located at B. So automatically, the extreme value theorem cannot hold. This function does have extreme values. It just, according to the extreme value theorem, it doesn't have to. But based off of this, if we take a look, there is no... I didn't want the pen there. I wanted the highlighter. There we go. There is, at this endpoint, there's no point there. So what's the highest point? Well, it's the one closest to it. But there's no way to talk about what's infinitesimally close to it. So you're just going to climb on down this function. Always move from left to right when you talk about functions. And again, the lowest point would be right here, but it's open. So there is no minimum here. But if you look at B, you jump up, and there's a point that in this immediate region, it is the highest of all the points. So x equals B, we're going to have a local or a relative maximum. And then as you continue moving on, we have a local maximum at C because in the immediate region here, it is the highest point. So at x equals B and x equals C, you've got local maxes or relative. Okay, but for a problem like this, there is no minimum. Now take a look at part B. Part B, again, in order for the extreme value theorem to hold, it's got to be continuous on a closed interval. And again, we've got an endpoint that's open, and we also have a discontinuity. So as you follow along this function, moving from left to right, there's no minimum value here because it would be infinitesimally close to A. So we're moving up. There would be a maximum here, but there's no point, so there's no max. Keep on moving. And now we come down to a minimum at C. Not only is this a local minimum, there's nothing lower in the immediate region, but if you look on the y-axis, there is no other point on the graph that's lower than this. So C is also going to be an absolute minimum. And then as you continue on the function, you've got point D here, which is, again, a local maximum. There's no region, there's no higher point in the immediate region, but it's also an extreme an absolute extreme because there's nothing higher in that entire function. So here we've got x equals c is going to be a absolute. You can also call it global minimum. And x equals d is going to be considered an absolute or global max. You should be comfortable with both terms. You'll see all of them. So I'm going to continue to try to use them just so you become more comfortable with them. Moving on to something called Rolle's theorem, and those of you that did the activity where you got to see Rolle firsthand, it's a pretty self-explanatory theorem. When you take the AP exam, you don't actually have to call it Rolle's theorem to defend your justification. Take a look. Rolle's theorem just says if you've got two numbers A and B that basically are defining your domain, if the function is continuous within that interval, including those points, and if the derivative exists at every single point within those two coordinate points, or those two x values, and if the y value at A and the y value at B both equal 0, then there's a number between the two of those where the derivative is 0. Okay, well, let's put all this. This is way too many words. This coordinate point here we'll call A. This coordinate point here we'll call B. There is no way that you can draw a continuous, smooth curve that doesn't have any corners, cusps, vertical asymptotes, meaning, okay, so part A, we're going to say there's no jumps. Part B of Rolle's theorem, we're going to say there's no corners, no cusps, or anything like that. And then part C is right here. We just showed that A is the y value is 0, and at B the y value is 0. There's no way to connect these two coordinate points and not have a derivative equal 0 somewhere in the interval, and there's actually 3 of them. We've got this point right here, we'll call C1. We've got this point right here at the little local maximum, we'll call C2. And then we've got this little minimum over here, we'll call C3. Again, it's pretty self-explanatory. There's no way to have this happen, but you know, Michel Rolle decided to put his name on it, so good for him, props. Okay, ordinarily I would just have you read on your own, but this next vocabulary word is so crucial and important that I'm actually going to read with you. So read with me, everybody. A critical point. It is a location in the interior of a domain. We are not talking endpoints. So it's within the interior of the domain at which the derivative equals 0 or the derivative fails to exist. If it's on the interior and the derivative is 0 or fails to exist, this is called a critical point. Okay? Not all critical points will be extreme values. And again, extreme values, as you remember from the first page because you read so closely, extreme values are where you've got maxes and mins. So here are two example graphs where you will have a critical point that's not an extrema. So here at x equals 0, the derivative at this location is 0. We would draw a horizontal tangent line in there, and we'll pretend that that hit that little plateau very nicely. So the derivative equals 0 there, but it's not an extrema. The derivative never changes signs before and after. You know, here you've got f prime greater than 0, and after f prime equals 0 at this location, again, f prime is greater than 0 again. So there's no switch in sign of the derivative, so this is not an extreme value. Likewise, on this little cube graph, we've got f prime greater than 0. Okay, the function is increasing, and then it's increasing after that. But for just a split second, right at this location, you've actually got a vertical tangent. The slope of vertical line is not defined, hence f prime is not defined. But again, here's another location where it's not an extrema. So both of those are considered critical points because they're on the interior and the derivative either is 0 or is not existing. But neither one of those was extreme values. So we're going to be talking about this a lot over the next couple days. Keep reading with me here. Extreme values can only occur. The only way you can have an extreme value is if you're talking about a critical point or an end point. Okay, let me just keep on circling this. Maybe you'll see it's very important. Okay. If you are trying to find maximum and minimums analytically, we're talking using algebraic manipulation given a function. The first step is to find the derivative of the function and determine where the derivative is 0 or undefined. So here we go. We're talking about those critical points. Then you're going to find the value of the function at each critical point. And from there, we're going to use the values of the slopes between the critical points to determine if we've got maxes or mins. So again, we're letting the derivative help us learn about the original function. If you have a closed interval, you're going to check endpoints as well. So we're going to do an example here, and I'm going to try to go a little bit slower on this, and go back and watch if you have to over and over again on this one, because this is going to start. Okay, Mr. Dillon is hitting my elbow. See, now you're in the video. How do you like that? All right. Okay. Find all extrema. So we're talking about, in order to find extrema, you've got to find critical points. And again, critical points, interior of the domains. And here we've got ourselves a nice little closed interval. So we're going to be checking endpoints as well. You can double check the function when we are done to ensure that, yes, our answers make sense. And I would actually encourage you to do that when you're practicing these as you get started here, to really relate the picture of the graph with what's going on with the derivative. Ties it all together nicely. Okay, I'm done rambling. Here we go. The first thing is, look at your original function. We don't have any discontinuities. This is a smooth, continuous function. There's no cusps or corners or anything like that. So we're good to go as far as that is concerned. First step was to take the derivative. So f prime of x, again, being very careful about notation. Take the derivative of this guy, you're going to get a 6x squared plus 12x. How nice for us. This is going to factor beautifully. It's almost like I planned it. So again, if you go back, and I'm going to slide this up here, you're trying to find the derivative where it equals 0 or is undefined. Again, the derivative function itself, this is a quadratic, so there are no discontinuities. It's never going to be undefined. So all we have to do is worry about where this thing is going to equal 0. So set the derivative equal to 0, and if you do that, you can also pull out a 6x here. You'll be left with an x plus 2. And zero product property says that either 0 equals 6x or 0 equals the x plus 2. And we're getting a value of x equals 0. Let me try that again. Let me find my eraser. This is supposed to be x. X equals 0, or you're getting x equals -2. Okay, so we've got two possible values for extreme values. These are just possible locations. These are critical points. So let's see if I can show how important this is, that you know this. These are critical points. Technically, only one of them is, and it's this guy. I'll give you $2 million if you can tell me why. What? No answers? Okay, well, I'll keep my money. It's because it's on the interior of the domain. This guy over here, this is the endpoint. Okay, so even though we got it by finding the derivative equal to 0, it's technically not a critical point because it's not on the interior. All right, moving along here. So we've got ourselves a little critical point. Now what I'm about to show you is called a number line for testing. Oh, I'm writing in red. I can't do that. Sorry. I work at Highland Park, not Deerfield. All right, let's go back to blue. So we're using a number line. And this number line is going to tell us information about the derivative. Note, I'm labeling my number line as x because this is telling me what numbers I'm testing. I've got a hard boundary here of -2. I can't go beyond that. I've also got a firm boundary of +1. Can't go beyond that guy. And I'm going to put any possible extreme values on this number line as well. So at x equals 0, which is right about cha, okay, I've got information about that. Now, above this, I'm going to show what's going on with the derivative. Okay, f prime of x. At x equals -2, it's 0. This thing is a flat tangent line. At x equals 0, we also have the derivative equal to 0. So again, another horizontal tangent. I don't really care about what's happening at x equals 1, and technically I didn't really care about what's happening at x equals -2. What I do care about is what's going on within the regions. You're going to know information about whether something is a maximum or a minimum based off of whether the function is increasing or decreasing. And you'll know that just based off of whether the derivative is positive or negative. So if you test a number in the region, and you'll know what's going on with the derivative. For example, in between x equals -2 and x equals 0, you can plug in an x equals -1. Go to your factored form over here. This was the factored form of the derivative. And if you plug in x equals -1, on the left-hand side, you're going to get a negative. On the right-hand side, you're going to get a positive. Negative times a positive. So overall, we're getting a negative value. Okay. So that's telling us that the derivative is negative. My question to you is, what does that tell you about the function? If your derivative is negative, your function is decreasing. Okay, so I'm going to draw a little f of x down here. So this is kind of like turning out to be kind of like a chart. So the function is decreasing. And let's find out what's going on in between x equals 0 and x equals 1 now. So take a value like a half. This is kind of like when we were evaluating limits as the limit was headed towards infinity. I don't technically care about the number that's coming out of this. I just care about whether it's positive or negative. So again, I want to know about what the value of the derivative is, so I'm plugging information into the derivative. And again, factored form is going to be easiest. So if you plug in a 1/2, you're getting a positive times a positive. I'm getting a positive. Again, don't care about the actual value, I just care that it's positive. So if your function, if the value of the derivative is positive, your function is increasing. Now, what does it look like if you have a negative slope moving to a positive slope? Something like this. I don't care about the exact shape. I care about the fact that this would have an end point. It would go down and have a nice smooth transition, and it would come up and it would have an end point. So what's going on here? Well, I've got I'm going to have to use red here. I've definitely got a maximum here. I've got a minimum here. And I've got a maximum here. All of this stuff, I'm outlining in red right now, is for your eyes only. AP graders do not look at this. Okay, so here's where it's going to be information for you to actually justify your work now. You need to know what the value is at f of -2. You're checking your minimum, or I'm sorry, your maximums. So f of -2, and you want to know what f of 1 is. These are values. These come from the y's. So these come from the f function. If you plug in -2, you're going to have 2 times -2 quantity cubed plus 6 times -2 quantity squared. Okay, and if you do this work, you're going to get a value of 8. That was like magic, huh? Do you like how that showed up? And then for f of 1, you're going to have 2. You're going to have 1 cubed plus 6 times the 1 squared. And you're going to get... Alright, cool. Hold on. I have to explain my panic a little bit. I hit the stop button instead of the pause, so I kind of freaked out thinking I recorded and then erased everything. Ah! Okay, so here's what's going on. We have two y values that actually ended up being the exact same. So because of that, within the region that's defined from -2 to +1, we have two y values that are the top y values within that domain. So we're going to call both of those absolute maxes. Every absolute max is also a local max, and it is possible, as we've just shown, to have two of them. I do not have to work to find out what the absolute min is, just based off of the fact that I know that at x equals 0, the function is decreasing before it and increasing after it, which makes it the only minimum within the region. But we can go ahead and show that the minimum, f of 0, is going to equal 0, and that is our only minimum, which makes it the absolute minimum. Okay, now I'm going to show you the justification that you would require here, and I'm going to see if I can squeeze it in over here. you would say that f, let me see, actually erase this part right here, hold on. You would say x equals -2 is an absolute min because f prime of x is greater, it's less than 0 for x greater than -2. And x equals 1 is an absolute min. Did I say min? I meant max. Oh, fiddlesticks. Go back. Go back. I know you guys are going to be cranky with me on that one. I meant to write max. Both of these are absolute maxes. Okay. So we've got x equals -2 is an absolute max because the derivative is less than 0. So the function is decreasing afterwards. And then at x equals 1, we've got an absolute max because f prime of x is actually greater than 0, which means the function's increasing up until that point for x less than 1. And for the same logic, you could say the same thing at x equals 0. You've got an absolute min because f prime of x is less than 0 for x less than 0, and f prime of x is greater than 0 for x greater than 0. Okay, and next time not only will I leave you more room, but we'll have time to actually talk about a little bit more of the justifications, but I want to start you off slow so you get comfortable with it. And I think I'm going to stop right here because this is becoming a very long video. Okay. So your little practice problem is going to be this guy on this page, and use analytic methods, so same thing we did on the previous example, to find the extreme values of the function on the interval and where they occur. And I actually didn't give you an interval for this one, so you don't have to check any endpoints. So all you have to do is find those critical values. Once you find the critical values, test the regions just like we did, and you can confirm your answer using your grapher. So until next time, au revoir.